Hello, my name is Álvaro and I'm going to talk about a Vitali covering theorem for Hausdorff-type measures in uniform spaces. By reviewing the literature, we can find at least two Vitali covering theorems, aside from the covering lemmas, one for the Lebesgue measure and the other for the Hausdorff measure. Both of them apply to Euclidean spaces, even though the second one could well be valid in a general metric space. However, there does not seem to be any concerning uniform spaces, which are a natural generalization of metric spaces. Here, we propose a version of this classical theorem for uniform spaces. We will begin by recalling the classical versions of these theorems. Then, we will recall the definition of uniform spaces and we will introduce the linearly uniformizable spaces. Next, we will recall a pre-existent Hausdorff-type measure for uniform spaces. This will make us propose a generalization of the diameter function. Next, we will talk about Vitali classes and how to translate them to uniform spaces. And finally, we present our main result. So, let's read the Vitali covering theorem for the Lebesgue measure. Let E be a measurable set, a Lebesgue measurable set with finite measure, and let V be a regular family of closed subset of R to the D, that is a Vitali covering of E. Then there exists a finite or countable infinite disjoint subcollection such that the point not covered by this subcollection have zero measure. On the other hand, we have the Vitali covering theorem for the Hausdorff measure, which says that if we have a set E of R to the D that is Hausdorff measurable, and we have and V is a Vitali class of closed subset for E, then there exists a finite or countable infinite disjoint subcollection such that either two options. It can be that the measure of the point not covered by this collection have zero measure, or that the sum of the powers of the diameters of this collection is infinite. We see that both classical Vitali covering theorems state that if we have a measurable set and a Vitali type covering of such set, we may select a countable or finite subfamily. It may be infinite uncountable or finite. So that subcollection covers almost all of the set, but in the case of the Lebesgue measure, it certainly covers almost all of the set. But in the Hausdorff measure, it may cover all of it, or the sum of the diameters is infinite. Thus, the version concerning the Lebesgue measure is stronger, but the one concerning the Hausdorff measure is more general, since it could well be valid in a general metric spaces and not only Euclidean spaces, because Hausdorff measure is defined on metric spaces, not only in R, in the real numbers. We now recall the definition of uniform spaces. A family of subsets of the product of an non-empty set X with itself is said to be a uniform structure if it is a filter. The diagonal is contained in its set. For each set, its inverse, defined this way, is also part of the uniformity, and a certain triangular inequality type property, this property in point 4, in item 4, is verified. These sets, the sets that form the uniform structure, are called entourages. This is the name they receive. And we say that a family of entourages is a family or a base of entourages if it is a base of filter of the corresponding uniform structure. Besides, every uniform structure induces a topology following this construction. Given a uniform space X, a subset A of X is open if and only if for each X in A there exists an entourage U such that u of x, defined this way, is contained in A. We may also define u of A, u of a subset, where u is an integer. And finally, a uniform space is said to be linearly uniformizable if it admits a base of integers previously defined that has a linear order with respect to inclusion. We show now two instances of linearly uniformizable spaces. The first one is the uniform structure derived from a metric. We have a metric space, and for each epsilon greater than 0, we define u sub epsilon this way: the set of points such that its distance is lower than epsilon. It is easily checked that this uniform structure, this family of sets is a uniform structure, and furthermore, they are ordered by inclusion, and thus it is a linearly uniformizable space. For the second one, we consider a non-empty set S and a well-ordered set I. We define these sets, this V sub beta, and it can be verified that they form a base of uniformity with a linear order. This order comes from the well order of I. So it is a linearly uniformizable space. We move on now to measure theory in uniform spaces. It is not deeply developed, the measure theory in uniform spaces, but fortunately it is not totally empty. Richard Wilmot proposed a Hausdorff-type measure for uniform spaces. It is constructed the following way. We take a uniform space, we take a family of subset of X, and we take a map tau that goes from that family of subset to R and the infinity. And it has to be non-negative, what we will call a premeasure. And given an integer u, we define this set. First of all, well, giving an integer u and a subset A of X, we define this u star. Then we define this mu sub u of A as this infimum, and then we define mu of A this way. We immediately observe that it naturally generalizes the Hausdorff measure for metric spaces. If we recall the definition of the Hausdorff measure, we just need to change, to switch, to take this tau and place there the diameter, well, a power of the diameter depending on the dimension of the Hausdorff measure. Here we are measuring the sets of the covering using that tau instead of the diameter. And the way of controlling the size of that sets, because in the Hausdorff measure we also use the diameter, here we use the integer. We say that the covering C is of size U because all of the sets of C are contained in this U star. So it can be proved that mu is an outer measure, and thus, if we define it only of measurable sets, it is a measure. The construction of the usual Hausdorff measure, as we commented before, this tau is a power of the diameter. However, we don't have a metric here, so we need to set some conditions on this tau so that mu has desirable properties. Wilmot proposes several conditions on tau, but we will only require these three. He proposes 5, I think it was 5, but we will only require these three. But in addition, we require these extra properties we developed by ourselves. We proposed, these are original of us. So giving a base of integers, we shall take that family of subset of this form, those u of x, where some u are are in the Rn ranges, when the U are Rn ranges. And we also require these two properties, 3, that's different 3, and property 4, which says that for each U in the base and each X, there exists a constant C of n that only depends on n, it doesn't depend on the entourage and neither on the point, on the X. And this inequality is verified for each U and each X. And as I said, this C of n only depends on n and is the same for every n. And also a sorting property that said that for each U and V two entourages and each X and Y, we have, if we have this inequality, then one of them is contained in the other. Next, we'll recall the definition of a Vitali class. Given a set E in a metric space X, a family of subset of X, V, is said to be a Vitali class if for each point from E there is some set in V having arbitrary small diameter. That is, for each epsilon greater than 0 there is a set S in V such that X is in S and also the diameter is below epsilon and not 0. This is defined in metric spaces, but we can extend this definition to uniform spaces this way. Giving a subset E of X, where XU is a uniform space, we say that V is a Vitali class for E if for each X in X, and in this case each U if entourage U, there exists some S in V such that X is in S, is not a singleton, is not only the point X, and S is of size U. It's the same as with metric spaces, but using entourages instead of the metric. And a trivial example is this one. Given a uniform space and an empty set E, we just take all the entourages and all the points. It's a trivial example. Besides, from now on, we will consider Vitali classes whose elements are of this form, where V is a symmetric entourage of a given base of uniformity. And we shall define an additional property between the relation of tau and mu. Given a uniform space, XU, we say that, we first define another property on a Vitali class. First of all, we need to define an initial property of a Vitali class. We say that a subset E of X admits a strongly upper tau closed Vitali class if there exists a Vitali class V such that for each finite family F of V, if we take this finite family, the remaining subset in the Vitali class, there is one of them that does not intersect any member of F, such that the supremum of the tau of the remaining set is reached in this point, in this set. And finally, we present our main result. First, nonetheless, we need an additional condition between tau and mu, the one I was commenting before. We will say that mu is exhaustively null with respect to tau if this implication is satisfied. That is, given a sequence of sets of these forms, where these are entourages of a given base of uniformity, we say that mu is exhaustively null if, when this condition happens, this sum is finite, then this limit tends to 0 as k tends to 0, and this is for every u in the base of uniformity. And we now do present our main result, that is the following. Given a uniform space endowed with a tau mu measure such that mu is exhaustively null with respect to tau, and given a set E of X, a subset E of X, if V is a strongly upper tau closed Vitali class for E, then we may select a disjoint, finite or countable subfamily such that either this happens, the sum of the tau of the subfamily is infinite, or the points not covered by the subfamily have zero measure. It's pretty similar to the version of the classical Hausdorff measure. The version of this theorem for the classical Hausdorff measure. In fact, we are going to compare the classical version with the usual Hausdorff measure and our version to see the similarities. The crucial difference is that we need the Vitali class to be strongly upper tau closed, in our case, for uniform spaces, and the reason for this comes from the proof of the theorem. The idea of the proof is of the classical version is to increase the size of some balls in order to capture some points not initially covered. We are taking out some sets of the Vitali class, but if we make bigger the ones remaining, we capture the points that may not be covered initially. But in uniform spaces, we lack some good properties of the metric, and thus we need a larger class of sets in order to guarantee that we capture all those points. But we are taking out some sets of the Vitali class. We need that the remaining are so many and so rich that we capture those points that otherwise would not be included. Therefore, even if the uniform version of this theorem is also valid for metric spaces and Euclidean spaces, the hypotheses are unnecessarily strong, but we cannot leave them out for uniform spaces. These are some of the references we used to the elaboration of this. There are some others, but these are the main ones. And thank you so much for your attention.